Alright, let's start by talking about what the Bellman equation actually represents. Here, the Bellman equation is the backbone of dynamic programming and reinforcement learning. What it does is quite elegant. It connects the value of a particular state to the values of the states that come after it. So instead of trying to solve a massive decision problem all at once, we break it down into smaller related decisions. Each of those decisions depends on what follows next. That's the recursive part. Each step builds on the previous ones. Okay, now there is a key idea here called the optimal substructure property. What is that? It basically means that if you can solve smaller parts of a problem optimally, you can combine those smaller optimal solutions into one big optimal solution. And this is why the Bellman equation forms the foundation of dynamic programming. It gives us a way to compute the best decision at every stage without looking at the entire decision tree from scratch. Okay, and you will often hear about something called the value function decomposition. What that means is we can express the value of being in a certain state as a combination of the immediate reward and the expected value of future states. This makes the problem recursive and computable step by step. And because we are working with Markovian decision processes, or MDPs, we are assuming that the next state only depends on the current state and the action we take now, not on the entire history. Okay, now on the practical side, the Bellman equation is not just some theoretical thing. Actually, it shows up everywhere. It's used in game AI, robotics, finance, logistics, you name it. In game AI, for example, it helps agents figure out the best move based on the possible outcomes of future moves. In resource allocation problems, it helps decide how to distribute limited resources for the best long-term result. And if you think about shortest path algorithms like Dijkstra's or A-star, they are essentially applying Bellman's principle in a simplified form. And in inventory management, it helps decide when to restock or how much to keep on hand to balance cost and demand. Okay, so to sum this first part, the Bellman equation is the mathematical tool that allows us to handle sequential decision making efficiently. It connects the present with the future in a way that can be computed iteratively. Without it, most of modern reinforcement learning would not even exist. And okay, now moving on to the Bellman principle, let's make sense of what those equations mean. When you see v of s equals expected return, written as like that, what that says is the value of being in a state is the total amount of reward you can expect to collect from that point onward. It's like saying, if I start here, how much am I going to gain on average until the process ends? Okay, then we have the action value function. And what is that? Q of s comma a state action value. Here, this one measures the expected return if we start in state S, take action A, and then continue following our policy. You can think of Q as being slightly more detailed. It doesn't just tell you how good the state is, it tells you how good a particular move from that state is. And finally, there is optimal policy. Here you can see pi star of s equals best action, and this one defines the rule that tells you which action to choose in each state to maximize your total reward. So here pi star gives you the direction, literally the best move to make if you want to perform optimally. So the core insight here is that the Bellman equation turns big complex problems into smaller manageable equations that can be solved step by step. By doing that, we can find the optimal strategy through iterative improvement instead of guessing or brute forcing it. Okay, so here we'll talk about value iteration algorithm. Looking at this section of the screen, you can see sliders for two key parameters. And what are they? Let's look at this. The discount factor gamma and the maximum number of iterations. And the discount factor written as like that here. Gamma equals here 0.9 tells us how much we care about future rewards compared to immediate ones. A value close to 1 means future rewards are almost as important as current ones. A smaller value means we prefer short-term gains. And when we run the value iteration process, what happens is we repeatedly apply the Bellman optimality equation to update the value of every state. At each step, the algorithm looks at all possible actions, calculates what the total expected reward would be, and updates the value to reflect the best one. Over time, these values stabilize. That's what we call convergence. Okay, and if you look at the convergence graph here, let me show you first here. The blue line represent the maximum, maybe might represent the maximum value among all states, and the green line might be the average value here, as you can see. And you can see both of them increasing as iterations go on. That's the algorithm learning, refining its estimates of how valuable each state is. Then at the bottom, you can see the bar chart of final state values. Each bar labeled S1, S2, and so on shows how much long-term return each state is worth after convergence. And here, the higher the bar, the better that state is in terms of total expected reward. So, through iteration, we have gone from random guesses about state values to stable, meaningful numbers that describe the system's optimal behavior. That's okay. And policy iteration is here. Let's look at here what's happening. This one follows a slightly different idea but achieves the same goal, finding the optimal policy. And it's built around two steps, policy evaluation and policy improvement. During policy evaluation, we calculate the value function under the current policy, which means we see how good our current strategy is. Then during policy improvement, we use those values to make a better policy, one that's greater with respect to those values. And when we run policy iteration, this back and forth process continues until policy stops changing. You can see, and on the chart, you can see how the policy value gradually converges. It starts somewhere around, what is that? Let's say 80 and slowly moves toward a stable point near 100, right? Yes, it is 94.7. Okay, and that's the algorithm saying, I have found a stable policy, no further improvement possible. And just below that, you can see the grid of optimal actions like arrows pointing up, down, left, or right for states S1 through S9. Each arrow shows the best move from that state under the final policy. So policy iteration doesn't directly compute values. It refines policies through repeated evaluation and improvement. And here Q-learning, we will see. Okay. Yes. So now Q-learning. This is a model-free approach, meaning it doesn't need to know the probabilities of state transitions or rewards in advance. Instead, it learns purely from experience by interacting with the environment. The two key parameters here are the learning rate alpha and the number of episodes. The learning rate controls how much new information overrides old information, A small alpha makes learning slow but stable. A large alpha makes it faster but noisier. And during training, the algorithm updates Q values, and here you can see, and each episode refines the agent's understanding of which actions lead to better long-term returns. So if you look at the chart here, you can see the average reward per episode gradually increasing, right? Let me show you slowly, and stops here. So it starts from negative value, and let's look, -50, and approaches a positive level as learning continues. That means the agent is moving from poor behavior to optimal behavior through repeated trial and error. That's okay, and here we will look at how Bellman's ideas apply in practice. So look at this. These concepts are not locked inside theoretical examples. They are used across many fields. In game theory and AI, algorithms based on Bellman equations help systems make strategic decisions. And think of chess engines like AlphaZero or Go playing AIs. They evaluate moves based on recursive value estimates, just like in value iteration. And in optimization and control, the Bellman equation guides how resources are allocated or how systems maintain stability. Power grids, for example, use dynamic programming to decide how to distribute energy efficiently. And financial portfolio management uses the same principle to balance risk and reward over time. And in machine learning, Bellman equations are the foundation of reinforcement learning. Autonomous vehicles use them to decide when to accelerate or brake. Robots use them to learn how to move and handle objects. Even recommendation systems rely on these ideas to predict which action, say which move succession, will lead to the highest user satisfaction in the long term.